Hey everyone, and welcome to The Explainer. I am absolutely thrilled to take you on a journey today into the fascinating and largely unseen investigative world of clinical microbiology. Being a medical detective isn't just about treating patients. It's really about tracking down these microscopic culprits that do literally everything in their power to hide from you. So today, we're opening up the playbook on one of the most notoriously elusive pathogens in human history, the bacterium that causes syphilis.
Picture this. You're working in a state-of-the-art microbiology lab. You've got the best tools, the most nutritious culture media, and the perfect incubators. But here's the catch. How do you diagnose a bacterium that flat-out refuses to grow in any of it? That's the exact dilemma we face with this unique microbial suspect. We can't just plate it on a petri dish and wait for it to multiply. We have to be much, much more clever than that.
All right, here's our game plan for today's explainer. We'll start with the elusive pathogen itself, look at direct microscopy visual clues, then move into non-treponemal screening tests, followed by treponemal confirmation tests, and wrap it all up with syphilis testing algorithms. Okay, let's dive right into Section 1, the elusive pathogen. Meet Treponema pallidum.
So the actual culprit behind syphilis is a bacterium called Treponema pallidum. Structurally, it's a spirochete, which basically means it's a very slender, flexible, spirally coiled bacillus measuring about 6 to 20 micrometers long. But here's the critical hurdle for us microbiologists. This thing is a master of evasion. It absolutely refuses to be cultivated on standard laboratory media, like blood agar or chocolate agar. In fact, for research and highly specific testing, the only way we can keep a live strain, specifically the Nichols strain, growing is by maintaining it in rabbit testes. Crazy, right? Because we can't just culture it from a patient's sample in a normal lab setting. We have to rely on completely different investigative methods.
Moving on to Section 2, direct microscopy, visual clues, catching the suspect in the act.
Remember how I said Treponema pallidum is incredibly slender? Well, it's actually too thin to be seen under a standard bright field light microscope, so we have to change the lighting entirely. By using a dark field condenser, we block out the direct light, which creates this hollow cone of light that only illuminates the specimen from the sides. And the result of this dark ground microscopy? We can actually watch the living, moving, bright spirochetes as they spiral and flex against a stark black background. It's a really brilliant workaround.
But what if we're dealing with fixed, dead tissues rather than a fresh wet mount? Well, we use an alternative trick. Since the bacteria are just too thin for normal stains, like a gram stain, we use a silver impregnation technique. Methods like the Fontana stain for fluid smears or the Lividiti stain for tissue sections literally deposit silver onto the surface of the bacteria. This physically thickens them up until they look like distinct black, coiled lines under the microscope.
All right, Section 3, non-treponemal screening tests, casting the broad dragnet.
To really grasp how we screen for this disease, we first have to talk about the reagent antibody. See, when Treponema pallidum damages human tissue, our body releases lipid materials from those damaged cells. The immune system reacts by producing antibodies against these lipids. We call these nonspecific antibodies reagent. So our primary screening tests aren't actually looking for the bacteria itself. They're looking for the collateral damage left behind in the body. This makes the dragnet highly sensitive, but as you'll see in a moment, it's very prone to catching innocent bystanders.
The most famous of these screening dragnets is the VDRL test, which stands for Venereal Disease Research Laboratory. Here's how it works. We take a heat-inactivated sample of the patient's serum and mix it with a highly specific antigen cocktail. And get this? It's made from an alcoholic extract of beef heart. Yes, literally beef heart, combined with lecithin and cholesterol. If the patient has reagent antibodies, they'll bind to this lipid antigen and create visible clumps, a process called flocculation. We then just look closely under a microscope to confirm the clumping.
Now, it's absolutely crucial to compare our two main screening tools, the older classic VDRL and its modern counterpart, the RPR, or Rapid Plasma Reagent Test. While VDRL requires you to heat the patient's sample and use a microscope to read the results, RPR uses carbon particles attached to the antigen. That allows you to see the black clumps with your naked eye on a simple plastic card, so no preheating or microscope required. However, as a microbiologist, you absolutely must remember this. If you're testing cerebral spinal fluid to diagnose a brain infection, like neurosyphilis, the VDR is still the strict drug of choice. RPR just cannot be used on CSF.
Now, remember how I mentioned this non-treponemal dragnet catches innocent bystanders? Because we're testing for antibodies against damaged lipids,
Any condition that causes tissue damage or massive immune shifts can trigger a biological false positive. Acute false positives, those lasting less than 6 months, can happen just from being in the first trimester of pregnancy or having a bout of malaria or even a viral infection. Chronic false positives can happen with autoimmune conditions like lupus or diseases like leprosy. Because of this, a positive VDRL or RPR is never enough to diagnose a patient on its own.
That brings us to Section 4, treponemal confirmation tests, the identity check.
If the screening tests are our dragnet, think of these specific tests as our sniper approach. Instead of looking for beef heart lipid reactions, these tests use actual Treponema pallidum antigens to see if the patient has antibodies directly aimed at the bacteria. The FTA-ABS test is the most sensitive and usually the very first test to turn positive after an infection. Historically, the TPI was the most specific, but it's totally obsolete now because, well, it literally required us to use those live bacteria from rabbit testes. Today, labs most commonly use TPHA or TPXA. These are simple, highly specific agglutination tests used to confirm if that initial VDRL hit was truly syphilis.
Finally, Section 5, syphilis testing algorithms, the master strategy.
So how do we put this all together? Well, the traditional two-step approach is the standard algorithm we've used for decades. Step 1. You screen with a cheap, highly sensitive VDRL or RPR to cast a wide net. If it's negative, you're good. The patient is likely clear. Step 2. If it's positive, you immediately confirm it with a specific treponemal test, like the TPA, to rule out a false positive from something like pregnancy. Step 3. If both are positive, you treat the patient, and then you follow up by monitoring their VDRL or RPR titers over the next year to make sure the medication actually worked.
But diagnostics have evolved. Today, there's a modern shift called the reverse sequence algorithm. As large commercial labs started processing thousands of samples a day, doing manual VDRL slide tests became incredibly tedious. So, in high-prevalence areas or massive lab facilities, they basically flipped the script entirely to rely on automation.
With this reverse logic, Step 1 uses a highly specific, fully automated treponemal test like an ELISA or CLIA machine. It's super fast and can process hundreds of tubes an hour. If that machine flags a positive, the lab moves to Step 2, running a quantitative VDRL or RPR. Why? Because we need to know if the disease is currently active. Now, if the automated test was positive but the VDRL is negative, you've got a discordance. So, Step 3 requires running a different specific test like the TPPA just to act as the final tiebreaker.
And that brings us to absolutely the most vital takeaway of this whole explainer. The reason we need both types of tests is this. Once you catch syphilis, the specific treponemal tests, like the TPPA or the automated ELISA, will essentially brand you for life. They almost always remain positive even after you are completely cured. But the non-treponemal tests, your VDRL and RPR, track current tissue damage. As the patient heals, those titers actively drop. Watching that VDRL titer fall by a 4-fold margin is exactly how we prove the medical detective actually solved the case and cured the patient.
So, as we wrap up today's explainer, I really want to leave you with this thought. We've seen how microbiology isn't just about throwing a sample on a dish. It's a highly calculated, structured game of cat and mouse, using dark field light, silver stains, beef heart extracts, and automated robotics. In a world where pathogens are constantly evolving and finding new ways to hide, understanding the tools in your diagnostic playbook is your absolute greatest weapon. Keep casting those dragnets, keep confirming those identities, and never stop investigating. Thanks for joining me today.